This electrostatics lecture is on electric potential. I'm Mrs. Estock. Let's get started. So far, we've made a lot of analogies between static electricity and gravity. We're going to start out talking about electric potential in the same way. It's a little bit easier to understand this in terms of gravity, and then this analogy can be applied to static electricity. Let's say that we have an apple some height above the earth. We know from experience that that apple would fall down, it would accelerate toward the earth. Well, what causes the mass of that apple to move? What causes masses within gravitational fields to be attracted? Well, we know that the mass of the earth has a gravitational field around it. So does the apple, but the apple's gravitational field is much, much smaller. And when the gravitational fields of two masses interact, there will be an attractive force of gravity between them. The earth has a gravitational field around it, so does the apple. And when those gravitational fields interact, that causes a force of attraction. That force of gravity, what we call the apple's weight, causes the apple to move. It will accelerate toward the earth. What if we take this idea and we apply it to charge? What causes a charge to move? Let's say we have a negatively charged balloon and we put that next to a Van de Graaff generator. We turn that Van de Graaff generator on and it acquires a positive charge on the metal sphere, the dome of the Van de Graaff generator. Well, from experience and what we've learned in class, we know that opposite charges attract. So how is this negatively charged balloon going to move? Well, it's going to be attracted to the Van de Graaff generator. Just like the apple moved toward the earth, this negative charge will move toward the positive Van de Graaff. Well, why? It has to do with electric fields. The charged sphere of the Van de Graaff generator exerts an electric force on the nearby balloon. The two electric fields interacting with each other exert an electric force. In this case, an attractive force because opposites attract. The charged sphere has an electric field around it, so does the negatively charged balloon. And the interaction of those two electric fields cause an electric force of attraction, which results in the balloon moving toward the positive charge. In fact, it accelerates toward the positive charge. We can relate this idea to potential energy. We say that an object with mass has gravitational potential energy if it's some height above the ground. And as that mass's height increases, its gravitational potential energy increases as well. Now, there's also a thing called electric potential energy. This is similar to gravitational potential energy. If you take an object with charge, let's say you have a positively charged object, and you bring it near a large negative charge, if you move that positive charge farther away or increase the distance or height between the positive object and the negative object, we say that its electric potential energy increases. If you were to release that positive charge, it would accelerate back naturally toward the negative charge. Just like with the gravity analogy, if you were to release a ball from some height above the ground, it will naturally accelerate down toward the earth. So again, with gravity, if something has some height above the earth, we say it has high potential energy. If we allow that object to fall down or decrease its height at least until the height is minimal or zero, we say that it has low potential energy. Now we can say the same thing about charges within an electric field. Let's say we have a positive test charge. If we bring that positive test charge near the positive plate, we would say it has high potential energy. If we allow it to go from the positive plate and accelerate toward the negative plate, At the negative plate, we would say it has low potential energy. So that's potential energy. But if you remember in our lab when we did the equipotential lines, we never called it potential energy, we just called it electric potential. So what's the difference between potential and potential energy? We're going to explain that in the next few slides. Again, let's start with the gravity analogy, and then we'll move to the static electricity examples. So what is the gravitational potential, and how is it related to gravitational potential energy? They sound the same, but they are slightly different. When we calculate gravitational potential, we're taking gravitational potential energy and dividing it by mass. Well, why would physicists do this? Why would you take potential energy and divide it by mass? What's the purpose of this? Well, let's take a look at an interesting thing about gravitational potential, and then you might be able to see its usefulness. Let's take a rock and we lift it 1 meter off the ground, and say this rock has 1 kilogram of mass. So a 1 kilogram rock at a height of 1 meter, if we calculated the potential energy as PE equals mgh, we would get 10 joules of potential energy. If we bring that rock up to a height of 2 meters, the same 1 kilogram rock, well, we're double the height but same mass, so now we have 20 joules of potential energy. Okay, so this is a bit of review. We can calculate potential energy just fine. What if we take another rock with more mass? Let's say a rock that has double the mass. Well, this rock that is 2 kilograms at a height of 2 meters now has double the potential energy. So they're both at the same location, but they have different energies. Is there a way we can make this number the same? In other words, what value can we give them if they're at the same location, that they would have the same number value here regardless of their mass? Well, potential energy changes with mass. We can see that 20 joules is different than 40 joules. But if we were to take their potential energy and divide out the mass, we could say they both have 20 joules per kilogram of potential at this location. For the lighter rock, 20 joules divided by 1 kilogram gives you 20. For the heavier rock, 40 joules of potential energy divided by 2 kilograms of mass also give you 20. This is what we mean when we say gravitational potential. It's a value that depends only on location, and regardless of mass, the potential is the same at that location. So it doesn't matter what mass you put at 2 meters, it's always going to have the same gravitational potential, the same energy per mass. Can we relate this to electric potential and electric potential energy? Let's give it a try. Now, electric potential energy does not depend on mass, rather it depends on charge. So let's say, in a similar example to the previous slide, we begin with 1 coulomb of charge at a distance of 1 meter from this positive plate. Well, we know this negative charge wants to be attracted to the positive plate. So the farther away from that positive plate you move the negative charge, the more potential energy it will have. If we move this negative charge up to a height of 2 meters away from the positive plate, well, 2 coulombs of charge at 2 meters, let's say it has 20 joules of electric potential energy. Okay, so we know that by changing the distance, you can change the electric potential energy of this charge. But again, let's see what happens when we double the amount of charge. If we put 2 coulombs of charge 2 meters away from that positive plate, we've effectively doubled the electric potential energy, just like we did in the previous problem by increasing mass. Well, now we have a negative charge that has double the amount of charge as where we started. And at the same location, we can see one has 20 joules of potential energy, the other has 40 joules. So by doubling the charge, we've doubled the potential energy. Physicists wanted to know, well, potential energy here changes with charge, but can we give a value for this particular location that is not affected by charge, that would be the same regardless of how much charge you put at this location? We can. It's called electric potential. If you take the potential energy and divide it by the amount of charge, this gives us a consistent value that stays the same regardless of charge. At this location, no matter what amount of charge you place here, the electric potential stays the same. We calculate electric potential by taking energy divided by charge. And this is something that we mapped out in our lab the other day. Electric potential, another word we give that, is voltage. Let's say we are mapping out the electric potential and finding equipotential lines surrounding a positive pole. Maybe you have a line that is 10 volts, one that is 8 volts. The farther away from that positive charge we're getting, the amount of electric potential is decreasing. Well, this is the equipotential line that we've mapped out in our lab. And let's say we place two charges, Q, and double that original charge, 2Q, on one of those equipotential lines. Even though these two charges are different, their electric potential is the same. If we measured the electric potential of both Q and Q2, it would give us 4 volts, or 4 joules per coulomb. This is electric potential. Even though the 2Q charge has more potential energy, it has the same electric potential as the 1Q charge. So by definition here, electric potential, the electric potential or voltage describes the amount of energy or potential energy stored in an electric field at a location in a way that is independent of the amount of charge, Q. Equipotential surfaces are surfaces on which all points have the same potential or voltage. Well, why did we do a whole lab on this? Well, let's again make an analogy between equipotential lines for charge and equipotential lines for mass. Surrounding the Earth, there are equipotential lines. At this point, and at this point, a mass would have the same gravitational potential. Let's say that this is where the moon orbits around the Earth, some distance around the Earth. Well, the moon doesn't have to do any work to stay on this equipotential line because you're not changing its potential. It would be like going up to a new height, climbing a hill or a mountain. If you were to jump up to a new equipotential line, you're at a new elevation, you're at a new height and a new gravitational potential energy. But as long as you stay on that same dotted line, you don't have to do any work. But as you jump up higher and higher, you need more and more potential energy. Well, what kind of object has the same shape but related to charge? Doesn't this kind of look like a diagram for an atom? What is it, the Bohr model for an atom with specific orbits around the nucleus? So around that positive nucleus, we have a negative electron. Well, the electron can stay in orbit around this equipotential line no matter where it orbits. As long as it stays on that dotted line, it doesn't have to do any work. It doesn't have to absorb any extra energy, maybe in the form of a photon, to bump it up to a higher energy level. And the more energy it absorbs, the higher its potential energy becomes, and it can jump up to a higher equipotential line or a higher energy state, as you might have heard in chemistry. So as long as it stays on that one dotted line and moves in a circle, no work is required to move that charge, so long as it moves at a constant speed. If it were to jump up to a higher equipotential, then some work would be required to do that. It would have to gain energy, or the opposite could happen as well. You could jump down to a lower energy state and give off energy in the process. So in our lab, we mapped out these equipotential lines. In the previous slide, we saw what it looks like around a pole or a circular point. But in our lab, we also saw what they looked like between two parallel plates. And since those equipotential lines ended up being parallel to the plates, when we drew in the electric field lines, they were perpendicular to the equipotential lines, and we started to see how that electric field between plates is mapped out. The electric field lines went from the positive plate to the negative plate. And the electric field between two oppositely charged parallel plates consists of field lines that are parallel as well. Now, these field lines end up being equally spaced. That equal spacing indicates that the electric field strength is the same no matter where you go between those plates. So you could be here, you could be here, you could be here. The electric field is the same no matter where you go between those plates. And if you place an electron or a proton inside of that electric field, because the electric field strength is the same everywhere, that proton or electron would feel the same size force no matter where it's located, so long as it's within that electric field between the plates. And this force causes that charged particle to accelerate. Accelerate in what direction? Well, to the plate of opposite sign, because it will be repelled from like charge and attracted to opposite charge. And it might look something like this. As soon as it enters the space between those parallel plates, I'll replay it for you as well, it's going to start to feel an electric force. In this case, because it's a positive charge, it will be repelled from positive and attracted to the negative plate, and will accelerate toward that negative plate. And again, as soon as it begins feeling that electric force, the size of that force stays the same throughout its acceleration. Well, okay, if there's a force being applied to this charged particle over a certain displacement, well, we know from our energy unit that a force causing a displacement results in work being done. This work being done to the charged particle changes its energy. The potential difference, or voltage, between 2 points in an electric field is equal to the work done, or the change in energy, per unit charge, as the charge is moved between the 2 points. We can represent this with an equation. If a charge is moved from one potential to another, aka through a potential difference, then you have to do work since the energy is changed. This is what voltage is. This is what potential difference is. When you were in your lab mapping out the potential difference using your voltmeter, you were measuring the potentials at two locations, and then your voltmeter was taking those two potentials and subtracting them from each other. Well, what causes a potential difference? Work per charge. If 1 joule of work is done to move 1 coulomb of charge between 2 points in an electric field, it creates a potential difference of 1 volt. So 1 volt, in other words, is 1 joule per coulomb. 1 joule of energy per coulomb of charge. If we try it out in a practice problem, let's say we're moving a charge of 3.2 times 10 to the negative 19 coulombs between points A and B in an electric field, and to do this requires 4.8 times 10 to the negative 18 joules of energy. Now we have really small powers of 10 here. We're not talking about a lot of charge or a lot of energy because we're looking at a single charge here. We have to calculate the potential difference between these points. potential difference or voltage is equal to work per charge. That much work, 4.8 times 10 to the negative 18 joules of work, divided by the amount of charge, 3.2 times 10 to the negative 19 coulombs, gives us 15 volts, or 15 joules per coulomb, as our potential difference. So to summarize, potential energy and electric potential are similar, but they're not the same thing. Potential energy is how much energy the object has, and it's measured in joules. Another name for potential energy, or a way you could figure it out, is the electrical energy or the work done. All of those have the same units, joules, but electric potential is a little different. Electric potential is energy per charge, so that no matter what the amount of charge at a given location, the electric potential will be the same. And another name we give for electric potential is voltage. Voltage is the difference in electric potentials from two locations. You measure the two potentials and then you subtract them to take the difference. And joules are too large a unit of energy for problems with electrons, atoms, or molecules. So there's one other unit that we have to introduce here. If we're talking individual electrons, the electron volt is the unit of energy that is more appropriate. So sometimes instead of joules, you'll see the unit electron volt. An electron volt is the energy required to move one electron through a potential difference of 1 volt. And this is given on your reference table as well. 1 eV, or 1 electron volt, is equal to 1.60 times 10 to the negative 19 joules. Sometimes you'll have to use that to do unit conversions. So it's important to keep your units straight here. Work and energy measured in joules, potential or potential difference measured in volts, or joules per coulomb. Charge, the SI unit for charge is the coulomb, or sometimes when dealing with small amounts of charge, you'll see elementary charge. Electric field strength is either in newtons per coulomb, or it can also be calculated in volts per meter. And the electron volt, which we just went over, is a unit of energy. And 1 eV is equal to 1.6 times 10 to the negative 19 joules.